Welcome to another journey through the unknown. Tonight, we drift into the questions that keep scientists awake, the puzzles that have no answers, the mysteries that remind us how much we still have to learn. From the smallest particles to the largest structures in space, from the depths of the ocean to the workings of our own minds, science has given us so much knowledge. Yet the universe holds its secrets close. These 100 mysteries span every field of human inquiry. Some may be solved in your lifetime. Others may remain forever beyond our grasp. But each one invites us to wonder, to question, to remain curious about the world we inhabit. So settle in, let your mind wander, and allow these unsolved questions to carry you gently towards sleep. Let's begin. We cannot explain why anything exists rather than nothing at all. This is perhaps the most fundamental question we can ask. Why is there a universe? Why are there stars, planets, atoms, and life? Why is there anything instead of absolute emptiness? Philosophy has wrestled with this for millennia, but science offers no answer. Physics can tell us how the universe behaves once it exists. Cosmology can trace its history back to the Big Bang. But the question of why there should be existence at all lies beyond the reach of telescopes and equations. Some suggest the universe emerged from quantum fluctuations, that nothingness is unstable and something must always arise. Others propose that our universe is one bubble in an infinite multiverse, each with its own laws. But these ideas only push the mystery back. Why should quantum fields exist? Why should a multiverse be possible? Perhaps existence is simply the default state, and nothingness is the impossibility. Or perhaps this question has no answer, lying forever outside the boundaries of what science can address. Every other mystery we will explore tonight rests on this one. Everything we see, everything we are, exists on a foundation we cannot explain. The universe had a beginning, but we cannot say what caused it. Nearly 14 billion years ago, space and time came into being. The universe burst forth from a state of unimaginable density and heat. We call this moment the Big Bang, but what actually caused it remains unknown. We can trace the universe's story back to fractions of a second after it began. We can measure the afterglow still filling space. We can watch galaxies rushing apart, carried by the expansion that started long ago. But the spark itself, the very first moment, eludes us. Some theories suggest the Big Bang emerged from quantum uncertainty, a random fluctuation that created everything. Others imagine a cycle of universes, each one collapsing and rebirthing in an eternal pattern. Still others propose that time itself began with the Big Bang, making the question of what came before meaningless. Our instruments can look far back in time, but they cannot pierce the veil of that first instant. The cause of the universe remains hidden, a mystery at the very beginning of everything. Time flows forward, but nothing in physics explains why it must. Every moment slides into the past. You remember yesterday, but not tomorrow. A cup falls and shatters, but broken pieces never leap back together. Heat flows from hot to cold, never the reverse. This one-way flow is called the arrow of time, and it governs every aspect of existence. Yet the fundamental laws of physics contain no such arrow. At the quantum level, particles can move forward or backward in time with equal ease. The equations work both ways. Nothing in them demands that time should have a direction. So why does it? Scientists often point to entropy, the tendency for disorder to increase. The universe began in a highly ordered state and has been spreading into chaos ever since. But this only raises another question. Why did the universe start with such low entropy? Some think the arrow of time emerges from how information spreads through the cosmos. Others believe it is tied to the expansion of space itself. But none of these answers feel complete. Time's forward march is the most obvious fact of existence, yet its origin remains one of physics' deepest puzzles. Most of the universe is invisible to us. When astronomers measure how galaxies rotate, something seems wrong. Stars at the edges move far too quickly. They should fly off into space, yet they remain bound. The only explanation is that most of the mass in galaxies is invisible. We call it dark matter, and it makes up roughly 85% of all matter in the universe. We cannot see dark matter. It does not emit, reflect, or absorb light. We know it exists only through its gravitational pull. It holds galaxies together. It bends the path of light from distant objects. It shaped the cosmic web of structure throughout space. But what is it? Decades of searching have produced no definitive answer. Some think dark matter is made of undiscovered particles that barely interact with ordinary matter. Others suggest it could be black holes formed in the early universe. Experiments buried deep underground wait to detect a dark matter particle, but so far none have. For now, this hidden mass, 5 times more abundant than everything we can see, remains invisible and unexplained. An unknown force is accelerating the expansion of the universe. In the late 20th century, astronomers studying distant supernovas made a shocking discovery. The universe is not just expanding. Its expansion is speeding up. Something is pushing space apart faster and faster. This mysterious force has been named dark energy, though the name reveals nothing about what it actually is. Dark energy makes up about 70% of everything in the universe, yet we have no idea what it is. One possibility is that empty space itself has energy, a constant pressure pushing outward. Another is that dark energy is a field that changes over time, growing stronger or weaker. Some theories suggest it points to new physics, perhaps indicating that our understanding of gravity is incomplete. The consequences of dark energy are profound. If it continues as it is, galaxies will eventually drift so far apart that the universe will become cold, dark, and empty. If it grows stronger, it might one day tear apart galaxies, stars, and even atoms. We can measure dark energy's effects, but we cannot explain its nature. It is the largest mystery in all of cosmology. The constants of nature seem fine-tuned for life, and we do not know why. The universe appears to be balanced on a knife edge. If gravity were slightly stronger, stars would burn out too quickly for life to evolve. If it were weaker, stars might never form at all. If the electromagnetic force were different by a tiny amount, atoms could not exist. Even small changes to the fundamental constants would make the universe lifeless. This is known as the fine-tuning problem, and it troubles physicists deeply. Why should the laws of nature have exactly the values they do? There is no obvious reason. One explanation is chance. With infinite universes, each having different constants, we simply happen to live in one where life is possible. Another is that some deeper principle, not yet discovered, determines these values. Or perhaps life is not as fragile as we think, and many different universes could support it. For now, we do not know. The universe feels strangely suited for our existence, and the reason why remains hidden. No one knows if the universe is infinite or finite. The observable universe is vast, stretching about 90 billion light-years across, but we can only see so far because light has had only so much time to reach us since the Big Bang. Beyond that horizon, space continues. But how far? One possibility is that the universe is infinite, stretching forever in all directions with no edge. If so, there may be an endless number of galaxies, stars, and worlds. Another possibility is that the universe is finite but unbounded, like the surface of a sphere. In such a universe, traveling far enough in one direction would eventually bring you back to where you started. Measurements of the cosmic microwave background, the faint afterglow of the Big Bang, suggest the universe is nearly flat. But this does not tell us whether it is infinite. The true size and shape of the universe remain unknown. What lies beyond the edge of what we can see is a mystery that may never be solved. Beyond the observable universe lies a region we can never know. When we look into space, we look back in time. The light from distant galaxies has traveled for billions of years to reach us. But there is a limit. Beyond a certain distance, the expansion of space has carried galaxies so far away that their light will never reach us. This defines the edge of the observable universe, but it is not a physical boundary. Space continues beyond it. Perhaps it continues forever. What exists in that unreachable expanse? It could be more of the same, galaxies and stars stretching endlessly. Or it could be radically different with regions where the laws of physics vary. Some theories suggest our observable universe is just one bubble in a far larger cosmos. If true, the vast majority of reality lies forever beyond our view. We are trapped on a cosmic island, able to see only the tiniest fraction of what may exist. There may be other universes, but we cannot prove it. The idea of a multiverse has captured the imagination of scientists and philosophers alike. It suggests that our universe is not alone, but one of countless others. Each universe might have different laws, different particles, even different numbers of dimensions. The concept arises naturally from certain theories. Inflation, the rapid expansion thought to have occurred just after the Big Bang, could create bubble universes, each budding off with unique properties. String theory predicts a vast landscape of possible realities. In such scenarios, our universe is simply one outcome among many. But there is a problem. If other universes exist beyond our cosmic horizon, we may never be able to observe them. No light or signal could cross the boundary. This makes the multiverse both fascinating and controversial. An idea we cannot test may never be more than speculation. Still, the possibility that reality extends far beyond our universe is one of the most provocative ideas in modern physics. Space and time may emerge from something deeper we have not discovered. Einstein showed us that space and time are not rigid backdrops, but flexible and dynamic. They curve, stretch, and warp in the presence of mass and energy. Yet, at the deepest level, we do not understand what space-time actually is. At small scales, general relativity and quantum mechanics clash. Relativity treats space-time as smooth and continuous. Quantum mechanics suggests everything should be grainy and uncertain. Reconciling these two pillars of physics is one of the greatest challenges in science. Some ideas propose that space-time is not fundamental at all. It may emerge from something more basic, perhaps networks of quantum information or patterns of entanglement. In this view, space and time are like the surface of water. and beneath lies a deeper reality we cannot yet perceive. Others wonder if time itself is an illusion, a construct arising from more fundamental processes. If so, our most basic intuitions about reality would need to be revised. What space and time truly are remains one of the most profound questions in science. A single particle can exist in multiple places at once, and we do not know how. Quantum mechanics tells us that before we observe a particle, it does not have a definite position. Instead, it exists in a superposition, occupying many places simultaneously. An electron can pass through two slits at once, interfering with itself like a wave. Only when we measure it does the particle settle into a single location. This is not just theory. Experiments have demonstrated superposition with particles, atoms, and even molecules. Scientists have created systems where objects exist in overlapping possibilities. Yet no one truly understands what this means. Does the particle physically exist in multiple places? Is superposition just a reflection of incomplete knowledge? Some interpretations suggest reality splits into parallel branches, one for each possible outcome. Others claim reality itself is indeterminate until measured. The ability of particles to exist in superposition remains one of the strangest and most unsettling features of the quantum world. Entangled particles influence each other across vast distances, defying explanation. When two particles become entangled, their properties become linked in a mysterious way. Measure one, and you instantly know the state of the other, no matter how far apart they are. This phenomenon troubled Einstein so much that he called it spooky action at a distance. It seemed to violate the cosmic speed limit. Nothing, not even information, should travel faster than light. Yet experiments confirm that entanglement is real. Photons, electrons, and even atoms have been entangled and separated by great distances. No signal appears to pass between them, yet the correlations remain perfect. What does this mean? Some physicists suggest the universe is non-local, connected in ways that transcend space and time. Others think entanglement points to hidden variables we have not yet discovered. Still others propose that information itself may be the foundation of reality. We use entanglement in quantum computing and secure communication, but we cannot explain why it works. The universe maintains connections across space that we still do not understand. Observation seems to affect reality, and no one knows why. One of the strangest discoveries in physics is that measurement changes the system being measured. In the double-slit experiment, particles behave like waves when unobserved, creating interference patterns. But if we measure which slit a particle passes through, the wave behavior disappears. The mere act of observation alters the outcome. Why should this be? One explanation is wave function collapse. The mathematical description of all possible states collapses into a single outcome when observed. But what counts as an observer? A measuring device? A conscious mind? Or something else entirely? Some interpretations say every possibility happens, branching into multiple universes. Others suggest particles only become definite when information about them becomes irreversible. None of these ideas have been proven. What we do know is that the boundary between observer and observed is not as clear as we once thought. The universe seems to respond to being watched, and no one knows why. Gravity is far weaker than the other forces, and we do not know why. Gravity shapes the cosmos. It holds planets in orbit, binds galaxies together, and governs the motion of stars. Yet compared to the other fundamental forces, it is astonishingly weak. A tiny magnet can lift a paperclip, overcoming the gravitational pull of the entire Earth. The electromagnetic force, the strong nuclear force, and the weak nuclear force are all vastly more powerful on small scales. Gravity, by comparison, is feeble. This is known as the hierarchy problem, and physicists have struggled to explain it for decades. One possibility is that gravity spreads into extra dimensions we cannot perceive, diluting its strength in our three-dimensional world. Another is that the true strength of gravity is hidden by physics we do not yet understand. Why gravity is so much weaker than the other forces is not just a curiosity. It is fundamental to the structure of the universe. Without this imbalance, stars could not form, galaxies could not exist, and life would be impossible. Einstein's relativity and quantum mechanics both work perfectly, yet they contradict each other. General relativity describes the universe at large scales with extraordinary precision. It explains how gravity works, how black holes form, and how space and time curve. Quantum mechanics governs the microscopic world with equal success. It predicts the behavior of atoms, particles, and light with astonishing accuracy. Both theories have been tested countless times, and both pass every experiment. Yet they cannot both be right. When physicists try to combine them, describing situations where both matter and gravity are quantum, the math breaks down. Infinities appear. The equations become meaningless. This happens inside black holes and in the first moments after the Big Bang, places where both gravity and quantum effects are strong. For decades, scientists have searched for a theory of everything that unites these two frameworks. Candidates like string theory and loop quantum gravity offer possibilities, but none have been confirmed by experiment. The fact that our two most successful theories describe incompatible realities is one of the great paradoxes of modern science. The center of a black hole remains unknowable. Black holes are regions where gravity is so intense that nothing can escape, not even light. According to general relativity, matter falling into a black hole is crushed toward the center, collapsing into a point of infinite density called a singularity. But infinity usually signals that our equations have failed. What truly exists at the heart of a black hole? Some believe the singularity is real, a place where the known laws of physics cease to apply. Others think a deeper theory, perhaps quantum gravity, will replace the singularity with something else, a finite core, a loop of space-time, or an entirely new kind of object. The event horizon seals the interior from view, so we cannot observe what happens inside. For now, the heart of a black hole remains one of the most inaccessible mysteries in all of science. We do not understand what singularities truly are. Singularities are places where our equations predict infinities. Infinite density, infinite curvature, time and space collapsing into something beyond definition. Black holes contain them. The Big Bang may have begun with one. But what are they really? Are singularities actual features of the universe? Or are they signs that our theories have reached their limits? Many physicists believe singularities point to the breakdown of general relativity. Somewhere beyond, a new theory that merges relativity with quantum mechanics must take over. In that theory, the infinities might dissolve into something finite and understandable. Until then, singularities remain puzzles at the edge of physics. They are places where our understanding stops, where our models break down. What lies beyond them is hidden, waiting for a deeper understanding of reality. Whether information is destroyed inside black holes is still debated. When matter falls into a black hole, it seems to vanish forever. But in physics, information about the state of a system is supposed to be conserved. So what happens to the information locked inside? Stephen Hawking showed that black holes can slowly evaporate through radiation. But if they vanish completely, where does the information go? If it is destroyed, the laws of quantum mechanics would be violated. If it escapes, then somehow the information must leak out through the Hawking radiation, a process no one fully understands. This puzzle, known as the black hole information paradox, has challenged physicists for decades. Some think the information is encoded on the event horizon itself. Others argue that black holes might connect to other regions of space-time, allowing information to escape. Still others believe our understanding of quantum mechanics may need revision. The fate of information in a black hole is one of the most important open questions at the intersection of gravity and quantum theory. Hawking radiation has never been observed. In the 1970s, Stephen Hawking made a groundbreaking prediction. Black holes are not completely black. Quantum effects near the event horizon should cause them to emit faint radiation. Over immense timescales, they would slowly lose mass and eventually evaporate. This radiation, now called Hawking radiation, is one of the most famous predictions in theoretical physics. Yet we have never seen it. Real black holes are surrounded by hot gas and violent activity that would overwhelm the faint glow of Hawking radiation. Detecting it directly may be impossible with current technology. Still, the idea has profound implications. It ties together quantum theory, gravity, and thermodynamics. It suggests black holes have temperature, that space-time is more dynamic than we realized. Laboratory experiments have created analogs using sound waves and fluids, but these are only indirect hints. Whether Hawking radiation truly exists remains unproven. If it does, it will transform our understanding of black holes. If it does not, something even stranger must be happening at the boundary of space-time. Black holes may be gateways to other regions of space-time. Black holes push our understanding of physics to its limits. Some solutions to Einstein's equations suggest that black holes could connect to other parts of the universe through tunnels called wormholes. In theory, entering a black hole might lead somewhere else, but this remains pure speculation. Wormholes, if they exist, might be wildly unstable. The intense gravity of a black hole could destroy anything trying to pass through. Yet the mathematics leaves the possibility open. Some physicists suggest that the singularity at a black hole center could be a bridge to a new universe with its own space and time. Others think black holes might recycle information, seeding the birth of new cosmic regions. For now, we cannot test these ideas. No signal can escape from inside a black hole's event horizon. Its secrets remain locked away. Still, the idea that black holes may be more than cosmic graves, that they could be portals to something beyond, is one of the most tantalizing mysteries in physics. We cannot explain how the first stars formed. When the universe was young, it was a dark, simple place. There were no galaxies, no planets, no complex chemistry. Only clouds of hydrogen and helium drifted through the expanding void. At some point, those clouds collapsed to form the first stars, ending the cosmic dark ages. But exactly how this happened remains unclear. These first stars, called population 3 stars, would have been enormous, hundreds of times more massive than our Sun. They would have burned hot and bright, living only a few million years before exploding in powerful supernovas. Those explosions seeded the cosmos with heavier elements, paving the way for later generations of stars and eventually for planets and life. The problem is, we have never observed one. No population 3 star has ever been detected. They lived and died so long ago that direct evidence is missing. Astronomers search for clues in the chemical composition of ancient stars, hoping to find traces of their violent births. The James Webb Space Telescope may finally glimpse their light. But for now, the exact process that ignited the first stars remains one of the great mysteries of astronomy. Some galaxies formed supermassive black holes too quickly. At the center of nearly every large galaxy sits a supermassive black hole, millions or billions of times more massive than the Sun. We understand how black holes grow by consuming gas, stars, and merging with other black holes. But in the early universe, astronomers have found black holes that grew far too large, far too fast. Some of these giants existed less than 1 billion years after the Big Bang. According to our models, there simply was not enough time for them to reach such enormous sizes through normal processes. This leaves a puzzle. Did they form directly from the collapse of massive primordial clouds? Did they arise from the deaths of the very first stars, which might have been much larger than we expect? Or is there a feeding mechanism we have not discovered yet? These ancient supermassive black holes challenge our understanding of galaxy evolution. If we can solve their mystery, we may unlock the story of how galaxies themselves came to be. No one knows why spiral galaxies are so common. When we picture galaxies, we often imagine spirals, sweeping arms of stars curling outward like cosmic pinwheels. Our own Milky Way is a spiral galaxy. But why should galaxies form such elegant structures? The answer is not entirely clear. One idea is that spiral arms are density waves, like traffic jams on a highway. Stars move through them, bunching up temporarily, creating the illusion of permanent arms. Another theory suggests that interactions between galaxies, gravitational tugs and disturbances, stir stars into spiral patterns. Computer simulations can reproduce spiral structures, but not with perfect consistency. Not all galaxies become spirals. Some are elliptical, shapeless blobs of stars. Others are irregular, chaotic, and formless. Why some galaxies develop beautiful spirals, while others do not remains an open question. When we look at the night sky and see the Milky Way stretched across it, we are looking from inside one of these mysteries. Fast radio bursts flash across the cosmos, and their origin is unknown. In 2007, astronomers detected a powerful burst of radio waves lasting only a few milliseconds. Since then, hundreds more have been found scattered across the sky. These signals, called fast radio bursts, release as much energy in a fraction of a second as the sun does in a year. What causes them? Some fast radio bursts repeat, suggesting they come from ongoing processes like magnetars, highly magnetized neutron stars that can flare with incredible energy. Others appear only once, hinting at catastrophic events like the collapse of a star or the merger of compact objects. But no single explanation fits all of them. Fast radio bursts travel across billions of light years. and the material between galaxies distorts them in ways that may help us map the structure of the universe. But until we identify their source, they remain cosmic riddles. Every so often, the universe sends us a brief, powerful signal. We can hear it, we can measure it, but we still do not know what is speaking. Pulsars keep time with astonishing precision, but their stability is not fully understood. Pulsars are the collapsed cores of massive stars, neutron stars that spin rapidly and sweep beams of radiation across space like cosmic lighthouses. Discovered in 1967, they were so regular that scientists briefly wondered if they might be signals from alien civilizations. Today, we know they are natural, but their precision remains remarkable. Some pulsars rotate hundreds of times per second without missing a beat. They keep time better than our best atomic clocks. How can an object so extreme, a star crushed to the size of a city, maintain such incredible stability? The answer lies in their extraordinary density and powerful magnetic fields, but the details are not fully understood. Pulsars can also glitch, suddenly changing their rotation speed in unpredictable ways. These glitches may come from processes deep within their cores, where matter exists in states unlike anything on Earth. Pulsars are laboratories of extreme physics, but they still hold secrets. Magnetars erupt with bursts of energy we do not fully understand. A magnetar is a type of neutron star with a magnetic field 1,000 times stronger than an ordinary neutron star and 1,000,000,000,000 times stronger than Earth's. These magnetic fields twist and snap, releasing sudden, violent bursts of radiation. In a single second, a magnetar can unleash more energy than the sun produces in 100,000 years. We detect these eruptions as intense X-ray and gamma-ray flares. But what triggers them? Are they caused by starquakes, fractures in the neutron star's crust under magnetic stress? Or are they due to sudden reconfigurations of the magnetic field itself, snapping like a cosmic rubber band? Some fast radio bursts have been linked to magnetars, suggesting they may explain at least some of those mysterious signals. But the full picture is still incomplete. Magnetars are rare, with only a few dozen known. They are reminders that the universe contains engines of energy we still struggle to comprehend. Cosmic rays strike Earth with incredible power, and we do not know where they come from. Every second, high-energy particles called cosmic rays bombard Earth from space. Most are protons traveling close to the speed of light. Many come from the sun or from supernova explosions, but some are so energetic that we have no idea where they originate. The most extreme cosmic rays carry the energy of a baseball thrown at high speed, packed into a single particle. No known process should be able to accelerate particles to such speeds. They may come from supermassive black holes, from the jets of active galaxies, or from exotic processes we do not yet understand. These particles crash into Earth's atmosphere, creating cascading showers of secondary particles that we can detect on the ground. Observatories around the world track them, trying to trace their paths back to their sources. But magnetic fields in space bend their trajectories, erasing the clues. Cosmic rays are constant visitors, yet their most powerful examples remain unexplained. Vast voids stretch across the universe, and their origins are unclear. The universe is not evenly filled with matter. Galaxies form a vast cosmic web, clusters and filaments, separated by enormous voids. Some of these voids span hundreds of millions of light years, nearly empty of galaxies. why are they there? Simulations suggest that gravity pulls matter into filaments, naturally leaving empty spaces behind. But the largest voids are bigger than models predict, raising questions about how they formed. Do they hint at new physics, perhaps revealing something about dark energy? Or are they just statistical extremes, rare but possible outcomes of cosmic structure formation? Voids affect how light travels through the universe and may offer clues about the nature of dark energy itself. But their true origins remain uncertain. Looking into a cosmic void is like staring into emptiness on the largest scale imaginable. They are among the loneliest places in existence. How the universe will end is still unknown. The universe had a beginning, but will it also have an end? Scientists consider several possibilities, each depending on the nature of dark energy and the balance of cosmic forces. In one scenario, the universe expands forever, cooling until stars burn out and galaxies fade into darkness. This is called heat death. In another, expansion may eventually reverse, pulling everything back together in a big crunch. A third possibility is the Big Rip, where dark energy grows stronger over time, tearing apart galaxies, stars, planets, and eventually even atoms. Which will it be? Current observations suggest expansion will continue, but the behavior of dark energy remains too uncertain to say for sure. The universe may last for trillions of years, or it may meet a more dramatic fate. For now, the ultimate future of everything remains one of the greatest unanswered questions in cosmology. Something triggered cosmic inflation, but no one knows what. In the earliest fraction of a second after the Big Bang, the universe is thought to have expanded faster than the speed of light in a process called inflation. This theory explains why the cosmos appears so smooth and uniform, and why tiny fluctuations eventually became the seeds of galaxies. But what caused inflation? That remains a mystery. Some theories propose a field of energy, the inflaton field, that briefly dominated the universe before decaying. Others suggest inflation is tied to the quantum structure of space-time itself. We see its fingerprints in the cosmic microwave background, where patterns match what inflation predicts. But the true cause, and whether inflation really happened as described, is still debated. Something made the universe grow unimaginably fast, setting the stage for everything that followed. But the spark that drove inflation is still unknown. The origin of life on Earth is still a mystery. Life on Earth began more than 3.5 billion years ago, but the details of its origin remain hidden. Fossil evidence shows that microorganisms were already thriving not long after the planet cooled. But how did non-living chemistry cross the threshold into life? One idea is that life began with simple molecules that could copy themselves, perhaps RNA before DNA evolved. Another is that life emerged near hydrothermal vents on the ocean floor, where hot water, minerals, and energy combined. Still others propose that life's building blocks arrived from space, carried on comets or asteroids. Each idea has support, but none are proven. Scientists have created amino acids and other basic molecules in laboratory conditions thought to resemble early Earth, but producing a fully living system remains beyond our reach. The origin of life may have been a unique event, or it may be a natural outcome whenever the right conditions exist. Until we find clearer evidence, the moment when chemistry first became biology remains one of science's deepest mysteries. We do not know if life began in the ocean or on land. Our planet offered many possible cradles for the first life. The ocean, covering much of Earth, seems like the obvious candidate. Hydrothermal vents, where hot water and minerals pour from the seafloor, provide energy and chemistry. Many scientists believe life may have begun there. But there is another possibility. Some researchers argue that shallow pools on land, subject to cycles of wetting and drying, could have concentrated molecules and driven the reactions needed to form life. Ultraviolet light from the sun, often destructive, might also have powered key steps. Both environments seem plausible. Each offers advantages and faces challenges. The ocean dilutes molecules, making interactions harder. Land-based pools may have been too unstable. Until stronger evidence emerges, we do not know whether life first stirred in the deep sea or in shallow waters on land. The answer is hidden in the deep past, in rocks long since transformed. No one knows how the first cells formed. Life is not just chemistry, it is organization. Modern cells are intricate structures, with membranes that separate inside from outside, and molecular machines carrying out countless reactions. But how did the first cell arise? One possibility is that fatty molecules naturally present on early Earth formed bubbles that trapped useful chemistry inside. These primitive membranes could have allowed molecules and energy to flow while protecting fragile chains of RNA or protein. Over time, the chemistry inside could have grown more complex, eventually becoming self-sustaining. Experiments show that simple membranes can form spontaneously under the right conditions. But the leap from primitive compartments to the complexity of a living cell is still unexplained. This transition from disordered chemistry to organized life remains one of the great mysteries of biology. Until we understand it, we cannot say how life truly began. DNA has a very specific shape, but why it took this form is unknown. All life on Earth uses the same molecule to store information, DNA. Its double helix structure is elegant and universal, carrying instructions for every organism. But why this molecule? Why this shape? Chemistry allows many possible ways to store information. RNA is simpler and may have come first. But somewhere in life's history, DNA became the master code. Its stability, its ability to replicate reliably, and its capacity to store vast amounts of information made it uniquely suited. Yet we do not know why DNA's specific structure, a double helix with precisely paired bases, became the solution all life depends on. Was it inevitable, dictated by chemistry? Or was it an accident, one successful outcome among many failures? The universality of DNA suggests it may be the best answer nature could find. Still, why life chose this exact path remains an open question. The origins of viruses are unclear. Viruses occupy a strange place in biology. They are not alive in the traditional sense. They cannot reproduce on their own and must hijack the machinery of living cells. Yet they are not merely inert molecules. They evolve, adapt, and shape the course of life on Earth. Where did they come from? Some scientists think viruses are relics from before cells evolved, survivors from an ancient RNA world. Others believe they began as pieces of genetic material that escaped from cells and learned to copy themselves. A third possibility is that they were once living organisms that became simplified over time. The truth may be that viruses arose in multiple ways, their origins as diverse as life itself. What is clear is that they are ancient and may have played a crucial role in evolution, by transferring genes between organisms. Viruses blur the line between life and non-life, and their beginnings remain one of biology's enduring mysteries. Some molecules became alive while countless others did not, and we do not know why. The early Earth was filled with chemistry. Simple molecules formed everywhere, from volcanic pools to lightning-struck atmospheres to deep-sea vents. Among them, some began to link into chains, but only a tiny fraction crossed the line into life. Why those molecules and not others? What property allowed some to organize into self-replicating systems? Was life inevitable once the right ingredients came together? Or was it a rare accident? Experiments show that many building blocks of life can form under natural conditions, but creating a self-sustaining evolving system remains elusive. The leap from chemistry to biology is vast. This uncertainty raises profound questions. If life is inevitable, the universe may be filled with living worlds. If it was a fluke, we may be utterly alone. The mystery of why some molecules became alive while others remained inert is one of the most important unanswered questions in all of science. We still do not know if life exists anywhere else in the universe. Earth is the only place we know where life exists. But with billions of stars in our galaxy and billions of galaxies beyond, it seems unlikely we are alone. Still, despite decades of searching, no clear evidence of extraterrestrial life has been found. We have discovered thousands of planets orbiting other stars, many in the habitable zone where liquid water could exist. We know organic molecules are common in space, found on comets, in interstellar clouds, and on distant moons. Mars shows signs of a wetter past. Europa and Enceladus hide oceans beneath their icy surfaces. Conditions for life seem abundant, yet the silence persists. We have not detected signals, found microbes on Mars, or uncovered alien fossils. It is possible life is common but hard to detect, or it may be exceedingly rare. Until we find even the simplest alien microbe, the question of whether life exists elsewhere remains unanswered. Could life form from completely different chemistry than ours? We do not know. All life on Earth is built on the same foundation: carbon, water, DNA, and proteins. But must it be so? Could life exist with entirely different chemistry? Some scientists think silicon, which can form long chains like carbon, could serve as the backbone of alien life. Others imagine organisms using ammonia instead of water, or exotic biochemistries thriving in methane seas like those on Saturn's moon Titan. Still others wonder if plasma, magnetic fields, or even information itself could host something resembling life. We do not yet know. All our definitions of life are shaped by a single example: Earth. It may be that carbon and water are the only real solution. Or it may be that the universe holds living systems stranger than we can imagine. If we discover alien life, it may look nothing like us. It could challenge our very definition of what it means to be alive. How common habitable worlds are remains uncertain. Astronomers have discovered thousands of planets orbiting other stars. Many are small and rocky. Some orbit in the habitable zone where liquid water might exist. But how many are truly habitable? That is still unknown. Habitability depends on more than distance from a star. Planets need the right atmosphere, magnetic protection from radiation, stable climates, and long-term geological activity. Some may be scorched by stellar flares. Others may be frozen or airless. Moons may be habitable too, with oceans beneath icy crusts, but we cannot yet measure them directly. The galaxy may be rich in habitable worlds, Or they may be rare jewels scattered across the cosmos. Right now, we cannot say. Each discovery brings us closer, but the true frequency of Earth-like conditions remains one of the great open questions in astronomy. We still cannot answer the oldest question of all. Are we alone? For as long as humans have looked at the stars, we have wondered whether life exists beyond Earth. Despite the vastness of the universe, despite the abundance of planets and the presence of organic chemistry across space, we still have no answer. We listen with radio telescopes. We send probes to nearby planets and moons. We analyze the atmospheres of distant worlds for signs of life. But so far, the silence is complete. It may be that life is common, but intelligent civilizations are rare or short-lived. It may be that life is rare at every level, and we are a singular accident. Or it may be that life is everywhere but hidden from us by distance or difference. The question remains open. Are we a lonely spark in a vast empty universe, or one voice in a cosmic chorus we have not yet heard? Until we find evidence, the answer remains unknown. Consciousness arises from the brain, but we do not know how. Every thought, every memory, every flicker of awareness seems to arise from the brain. Scientists can measure electrical signals moving across neurons. They can turn awareness off with anesthesia. They can track brain activity when you see an image or hear a sound. Yet none of this explains why there is an inner experience at all. Why should firing neurons create the feeling of being alive? A brain scan can show activity in the visual cortex when you see a sunset, but it does not explain why that experience comes with the sensation of color inside your mind. It shows circuits for sound, but it does not explain why hearing music feels moving. Researchers have ideas that consciousness appears when information integrates across the brain, that it emerges when neurons form certain patterns, that awareness may be a fundamental property of the universe itself. But none of these truly explain the leap from matter to mind. Consciousness is the most ordinary thing. It is what you are experiencing right now. Yet when we try to explain it, the answer slips away. Dreams fill our nights, but their purpose is unknown. Every night as you sleep, your mind creates worlds. Some are vivid, filled with people and places you know. Others are strange and fragmented, dissolving as soon as you wake. These are dreams, and though we all experience them, no one truly knows why. Some scientists think dreams help the brain process memories, strengthening useful connections and discarding irrelevant information. Others believe dreams regulate emotion, allowing you to work through fear, sadness, or conflict in a safe space. Some suggest they are simply random firings of a sleeping brain, patched together into stories. What makes dreams puzzling is their intensity. A nightmare can wake you in terror even though you are safe in bed. A good dream can lift your mood for hours. Sometimes dreams even solve problems. Artists, writers, and scientists have described breakthroughs that came to them in sleep. We know the brain is active while we dream, especially during REM sleep when the eyes flicker beneath closed lids. But the purpose behind it remains elusive. Dreams are nightly journeys into strange lands, yet their true meaning is still hidden. Time feels slower or faster, depending on our state, and no one knows why. Think of a moment when time seemed to stretch, a near accident, a sudden fright, an intense experience where every second felt like minutes. Now, think of the opposite. A day that seemed to vanish in an instant, hours that disappeared when you were absorbed in something you loved. Clock time is steady, but our perception of it is anything but. Why? No one knows for sure. Some believe the brain has an internal clock and that emotions like fear speed it up while calm slows it down. Others suggest the brain judges time by the number of events it processes. A moment filled with new details feels longer. A routine moment feels shorter. This could explain why childhood summers seemed endless, while adult years slip past quickly. Novelty stretches perception. Routine compresses it. But this is only a theory. What we do know is that time in the mind is elastic. It stretches, contracts, and sometimes seems to stand still. The seconds are constant, but our experience of them flows according to rules we do not yet understand. We do not understand how memories are stored and recalled. Your entire life, your first day of school, your happiest moments, your deepest regrets, is stored somewhere inside your brain. Yet how those memories are kept and how they return when you need them is still mysterious. Scientists know that memories are not like files in a drawer. They are patterns of activity across many neurons, spread across different regions. The hippocampus acts as a kind of index, weaving these patterns together. But exactly how the brain encodes a memory and later retrieves it is not fully understood. Sometimes memories change when we recall them, being reshaped before they are stored again. Sometimes we even create false memories that feel completely real. Why do some memories last a lifetime, while others fade in days? Why does a certain smell suddenly unlock a vivid scene from childhood? Experiments show glimpses. Neurons that fire when a specific face is seen. Brain activity that mirrors memory recall, but the full picture is missing. Memory is what makes us who we are, yet the machinery behind it remains unknown. Our emotions run deep, but their origins are mysterious. Emotions shape every part of life. Joy pushes us forward. Fear holds us back. Anger flares. Sadness weighs heavy. But where do they come from? Scientists know emotions involve both the body and the brain. Your heart races when you are afraid. Your stomach knots when you are anxious. Tears well up when you are sad. But the origins of these feelings are still debated. Are emotions hardwired? Ancient survival tools built into our biology? Or are they constructed by the brain, shaped by culture, memory, and interpretation? We know certain brain regions play a role. The amygdala for fear, the insula for disgust, the prefrontal cortex for regulation. But no single emotion center exists. Music can bring chills. Scents can trigger sudden nostalgia. Sometimes we do not even know why we feel the way we do. Emotions are powerful guides, steering our choices often more than reason does. Yet, the way they arise, the way they take hold of body and mind, remains one of the most intimate mysteries of being human. Creativity appears in sudden sparks, but we do not know where it comes from. An artist stares at a blank canvas, a writer at an empty page, a scientist at an unsolved problem. Hours may pass with nothing. Then suddenly an idea arrives. Clear, surprising, alive. Where did it come from? Creativity feels like a spark, but its origin is hidden. Some say it is the brain mixing and matching old ideas in new ways. Others think it requires stepping away, letting the subconscious work while the conscious mind rests. Many breakthroughs in history have come not at desks, but in dreams, showers, or quiet walks. Brain scans suggest different networks are involved, some generating ideas, others judging them. But this does not explain the moment of inspiration. Why does the solution arrive suddenly with such force? Why do some people overflow with creative ideas while others struggle? Creativity is one of humanity's greatest gifts, shaping art, science, and progress. Yet the place where ideas come from, that quiet leap from nothing to something, is a mystery we still cannot explain. Déjà vu makes the present feel repeated, and no one knows why. You step into a room you have never been in before, and suddenly everything feels strangely familiar. You sense you know what will happen next, though you do not. This is déjà vu, and it remains one of the strangest mysteries of the mind. Scientists suggest it may be a trick of memory. Perhaps the brain misfires, creating a false signal of familiarity without a real memory behind it. Others think it happens when one part of the brain processes an experience slightly before another, making the moment feel like a repeat. Still others suggest it comes from similarities between a current scene and a forgotten past one, fooling the mind. What makes déjà vu mysterious is its intensity. For a few seconds, reality feels doubled, both new and remembered. Almost everyone experiences it, yet no one can predict when or why. Déjà vu reminds us that memory and perception are fragile, and that the brain sometimes tricks us in ways we do not yet understand. Placebos can heal, but the power behind them is still mysterious. Imagine taking a pill, being told it will ease your pain, and then actually feeling better, even though the pill contained nothing at all. This is the placebo effect, and it is real. Doctors have seen placebos reduce pain, ease depression, and calm symptoms of disease. The effect is thought to come from expectation. The belief that something will help triggers real changes in the brain and body. Placebos can release natural painkillers, alter brain chemistry, and affect the immune system. What makes the placebo strange is that it can work even when people know they are taking one. Somehow, the ritual of treatment, the pill, the doctor, the belief taps into hidden healing pathways. But why some people respond strongly and others do not is still unknown. The placebo effect blurs the line between mind and body, showing us that belief itself can heal in ways we still do not fully understand. We do not know why we need sleep at all. Every night, we surrender to sleep. We close our eyes, drift into dreams, and lose awareness for hours. But why do we need it? Sleep is dangerous if you think about it. In the wild, an animal that sleeps is vulnerable. Yet every species does it in some form, suggesting sleep is essential. But essential for what? Some scientists believe sleep helps the brain store memories and learn. Others think it clears away waste, cleaning the brain of harmful buildup. Sleep may restore energy, regulate emotions, and strengthen the immune system. It may help the brain rewire itself, keeping connections balanced. Yet no single explanation fits all the evidence. Different animals sleep in different ways. Dolphins sleep with only half their brain at a time. Some birds sleep while flying. Some creatures need very little sleep at all. What we know for sure is that without sleep, minds and bodies quickly break down. Why we spend a third of our lives doing it remains one of science's great mysteries. We still do not know why aging happens the way it does. Every living being on Earth ages. Skin wrinkles, hair turns gray, muscles weaken. Eventually, the body begins to fail. But science cannot fully explain why aging happens or why it unfolds so differently across species. One explanation points to DNA. Each time a cell divides, the protective caps at the ends of chromosomes, called telomeres, grow shorter. Eventually, the cell stops dividing. Another theory blames accumulated damage. Oxygen molecules and other byproducts slowly corrode cells over time, leaving scars. Others see aging as an evolutionary trade-off. Energy is focused on reproduction in youth, leaving the body vulnerable later. Yet, nature presents exceptions. Some turtles and fish show almost no signs of aging. Certain jellyfish can revert to earlier life stages, sidestepping decline. Naked mole rats live far longer than similar rodents, showing resistance to age-related diseases. Why do some creatures resist aging while humans succumb? The answers remain elusive. Unlocking this mystery could transform medicine. But for now, aging is a riddle written into our cells. The limits of human lifespan remain uncertain. The longest confirmed human life ended at 122 years. But was this the upper limit of human biology, or just a remarkable outlier? No one knows. Some researchers argue humans have a hard limit. Beyond a certain age, the body cannot repair itself quickly enough. Evidence suggests survival rates decline sharply after 110, hinting at a biological cap. Others insist there is no strict maximum, only ever-rising odds of frailty and disease. What is puzzling is that although average life expectancy has climbed dramatically thanks to medicine and sanitation, the maximum lifespan has barely budged. Almost no one lives past 115, no matter where or when. Still, scientists search for ways to extend life further. They study families who remain healthy into extreme old age. They look for genes that resist disease. They test drugs that slow aging in animals. Could humans someday reach 150 years, or even 200? The data offers hints, but no certainty. The upper boundary of human life remains hidden. Some animals can regrow entire limbs, and we cannot explain how. If a salamander loses a leg, it grows a new one. If a starfish loses an arm, it slowly rebuilds it. Even certain worms can regenerate an entire body from a single fragment. In nature, regeneration is surprisingly common. But humans cannot do it except in the tiniest ways. A fingertip might regrow in a child, but a lost limb never returns. Why them and not us? Scientists studying salamanders find that when they are injured, cells near the wound seem to reset, rolling back into a flexible state like embryonic cells. From there, the cells grow into muscle, bone, and nerve, perfectly organized. Humans share many of the same genes, yet our bodies do not use them the same way. If we could unlock this ability, medicine would be transformed. Damaged hearts could heal themselves. Spinal cords could regrow. Limbs could return. Despite decades of study, the full blueprint of regeneration remains hidden. Why nature allowed some creatures this power while denying it to us is a mystery. Certain creatures live far longer than expected, and we do not know why. Most animals follow a simple pattern. Small bodies live short lives. Large ones live longer. Mice live a few years. Elephants live many decades. But scattered across nature are creatures that defy these rules. The Greenland shark glides beneath Arctic ice for centuries, living more than 400 years. Bowhead whales sing in frozen seas for over 2 centuries. Tiny, naked mole rats live 10 times longer than similar rodents with remarkable resistance to disease. Some clams have been found alive after more than 500 years. Why? Scientists have found clues. Unusual proteins that resist damage. DNA repair systems that seem more efficient. metabolisms that move incredibly slowly, but no single answer explains them all. Each species seems to have its own key to longevity, and humans cannot yet copy it. These creatures remind us that aging is not a fixed law, but a puzzle with many solutions. If we could learn their secrets, we might extend our own lives. For now, they remain timeless enigmas. Some animals survive being frozen solid, yet their secrets remain hidden. Imagine being frozen into ice, your blood crystallized, your heart silent, your body rigid. For most creatures, this means death, but not for all. The wood frog of North America freezes solid in winter. Its heart stops, its body stiffens, yet when spring warmth returns, the frog thaws and hops away unharmed. Certain insects and fish can do the same. Tardigrades, tiny water bears, can endure extremes far beyond freezing, surviving even in the vacuum of space. How do they do it? Some creatures fill their bodies with special molecules that act like antifreeze, preventing ice crystals from shredding their cells. Others use sugars that stabilize tissues during freezing. But the exact details of how their brains, hearts, and organs survive months without activity remain unclear. If we could master this trick, it might change organ transplants, medicine, even space travel. We could preserve organs for months. We could place humans into hibernation for long journeys. But for now, the secret belongs to these hardy survivors. Whales live for centuries with little cancer, and no one knows how. The bowhead whale can live for more than 200 years, gliding through icy Arctic waters. What makes this astonishing is not just its age, but its health. Despite its massive size, with billions of cells and centuries of time for mutations, cancer is remarkably rare. This is known as Peto's paradox. Larger animals with more cells should, in theory, have higher cancer rates. But whales, elephants, and other giants do not. Somehow, they resist. In elephants, researchers have found extra copies of tumor suppressor genes, like extra layers of defense. In whales, the explanation is less clear. Perhaps their DNA repair systems are unusually strong. Perhaps their metabolism slows damage. Perhaps they have unique biological pathways we have not discovered yet. If we could unlock this mystery, it might revolutionize cancer treatment for humans. Whales have cracked part of the code of long life without disease, but for now, their secret drifts beneath the waves. Birds can sense Earth's magnetic field, but the mechanism is still unclear. Every year, birds migrate across continents. Tiny warblers fly from Europe to Africa. Arctic terns cross oceans, circling the globe. They travel thousands of miles with uncanny accuracy. Part of their secret seems to lie in Earth's magnetic field, but how they sense it remains uncertain. Some evidence points to tiny crystals of magnetite in their bodies, acting as internal compasses. Other research suggests certain proteins in their eyes may let them see magnetic fields as faint patterns of light. But no single theory explains it all. What we do know is that their ability is incredibly precise. Even on cloudy days when the sun and stars are hidden, birds stay on course. Released in unfamiliar lands, they still find their way. It is a sense humans lack, like an invisible layer of reality we cannot perceive. For birds, the world carries directions written into its very fabric. Monarch butterflies navigate continents with a map we cannot read. Every autumn, fragile monarch butterflies begin an impossible journey. They fly thousands of miles from the northern United States and Canada to a few mountain forests in central Mexico. There, they gather in dense swarms, covering trees in shimmering orange. What makes this migration astounding is that no single butterfly completes the round trip. The ones that return north in spring are several generations removed from those that left in fall. Yet somehow, they arrive at the very same groves year after year. Scientists, no monarchs, use the sun as a compass, adjusting for the time of day. They may also sense Earth's magnetic field. But how they pass this knowledge between generations, how a butterfly that has never made the journey knows exactly where to go, remains a mystery. It is one of the most breathtaking migrations on Earth, guided by a hidden map no human has ever read. Migrating animals cross thousands of miles, but we do not know how they guide themselves. The natural world is full of great migrations. Salmon hatch in mountain streams, swim to the sea, and years later return to the same stream to spawn. Sea turtles crawl from the ocean onto the very beach where they first hatched. Birds, whales, and insects all travel across the planet with astonishing accuracy. Scientists have discovered clues. Some animals use the stars, the sun, and the tilt of Earth's axis. Some may follow magnetic fields or subtle scents, yet none of these explanations fully account for their precision. How does a bird find the same tree each year? How does a turtle cross an entire ocean to one patch of sand? These journeys remain partly unexplained, guided by senses we do not yet fully understand. Migration is one of life's oldest rhythms, a grand, mysterious dance written into instinct. Homing pigeons return home from anywhere, and the mystery persists. For centuries, humans have marveled at homing pigeons. Release one hundreds of miles from home, and it will rise into the sky, circle, and fly straight back to its loft. No map, no guide, just a hidden sense of direction. Researchers have proposed explanations. Some believe pigeons use the sun as a compass, adjusting for time. Others suggest they detect Earth's magnetic field, like a built-in navigation system. Still others point to smell, the idea that pigeons build a scent map of their home region. But none of these fully explain their uncanny accuracy. Even when released in strange places under cloudy skies, pigeons still find home. It is a mystery hidden in their biology, a secret compass we have yet to uncover. For pigeons, the world is filled with invisible cues. For us, it remains a puzzle. No one knows exactly how humans first developed language. Language is what makes us human. With it, we share ideas, pass down stories, and build civilizations. But how it began remains one of the greatest mysteries of our past. Our closest relatives, chimpanzees and bonobos, can communicate with gestures and sounds. But none come close to the complexity of human speech. At some point, our ancestors made the leap from simple calls to structured language with grammar, abstraction, and infinite possibilities. But when and how? Some theories suggest language began as hand signals, with words coming later. Others propose that rhythmic sounds, chants, and songs gradually evolved into speech. Archaeology shows us carvings and symbolic art tens of thousands of years old, suggesting the minds that created them were capable of complex communication. But the sounds themselves left no trace. Language allows us to describe what is not present, to plan, to dream, to imagine. It is both a survival tool and a window into thought. Yet the first spark of language, the moment humans first spoke, is lost in time. Laughter is universal, but its roots remain a puzzle. Wherever you go in the world, people laugh. The sound crosses cultures, ages, and languages. Babies laugh long before they speak. Groups laugh together. their joy contagious. Yet why we laugh and how it evolved remains uncertain. Some scientists believe laughter began as a signal of safety. Early humans may have laughed to show others that a threat had passed, turning fear into relief. Others trace it back to primates at play, whose panting sounds during wrestling resemble laughter's rhythm. But laughter is more than a survival tool. It lowers stress, bonds groups, and releases chemicals that flood the body with calm. Strangely, we laugh not only at jokes, but also at relief, at awkwardness, even at sorrow. Sometimes laughter bursts out when it makes no sense. Why should a sound, a breathy burst of air, carry such power? We do not know. What we do know is that laughter is ancient, universal, and mysterious. Music moves us deeply, but science cannot explain why. A melody can make us cry. A rhythm can make our hearts race. A song can bind us to memories we thought forgotten. Music has no obvious survival function, yet it shapes human life across every culture. Why? We do not know. Some suggest music evolved as social glue, binding early communities through dance and song. Others think it began as courtship, a way to signal vitality and skill. Still others argue it is a byproduct of language and memory, a beautiful accident of evolution. What makes music strange is its power. Stroke patients who struggle to speak can still sing. People with dementia recall lyrics when almost everything else has faded. Music can synchronize heartbeats in groups, can calm newborns, can stir armies to march. Why should organized sound reach so deeply into our minds and bodies? Science has no clear answer. Music remains one of the most universal, mysterious forces in human life. Love is powerful and complex, but its full nature is still unknown. Love shapes human lives more than almost anything else. It binds parents to children, partners to one another, friends across time. It inspires art, sacrifice, and joy. Yet science still cannot fully explain what love is. Biology shows us pieces. Love floods the brain with dopamine and oxytocin, chemicals tied to reward and bonding. Evolutionary theory suggests it developed to keep parents together long enough to raise vulnerable offspring. But these explanations do not capture the full experience. Why does love sometimes arrive suddenly, overwhelming us? Why does it last a lifetime in some cases and fade in others? Why do people risk everything for it, even against reason? Love is not only chemistry or instinct. It is memory, story, imagination, and something more. We can map its effects in the brain, but not its meaning. Love is both universal and unique, an experience shared across humanity, yet different for every person. Humans cry tears of emotion, and no one knows why. Tears protect our eyes, washing away dust and irritants. But only humans shed tears for reasons beyond biology. When we are sad, joyful, frustrated, or overwhelmed with laughter. Why? One idea is that tears are a social signal, showing vulnerability and drawing empathy. Another suggests they release stress chemicals, though evidence is mixed. Tears may strengthen bonds, making emotions visible to others. What deepens the mystery is that we cry for opposite feelings. Tears come with grief and with joy, with sorrow and with relief. They fall silently in solitude or in the middle of laughter. No single explanation captures all of this. Tears remind us that we are emotional beings, not just logical ones. They make the invisible visible, carrying feelings from inside to the outside world. But the reason humans alone evolved this response remains unsolved. Myths appear across cultures in similar forms for reasons we do not understand. From deserts to islands, mountains to forests, cultures separated by oceans tell stories that echo one another. Myths of great floods, of sky gods, of tricksters, of underworlds. They appear again and again. Why? Some suggest human minds are wired for story and certain themes arise naturally from shared experience. The fear of death, the hope for renewal, the awe of the sky. Others believe ancient myths spread through migration and trade, leaving echoes in distant lands. Still others wonder if myths are shaped by deeper patterns in the human brain, symbols born from the same inner landscape. Whatever the reason, myths carry truths that cultures find important. They explain the unexplainable, bind communities together, and pass wisdom through generations. But the strange recurrence of similar stories across the globe, appearing where no contact seems possible, remains a mystery. We often cooperate with strangers, and the origins of this instinct are unclear. Humans are unusual among animals. We not only help family and close allies, but also strangers. We donate blood. We build communities. We risk ourselves for people we may never meet. Why? Evolutionary theories suggest cooperation evolved to strengthen groups, giving them an edge. Others point to reciprocal altruism, the idea that help given will one day be returned. But humans go beyond calculation. We volunteer, we share, we sacrifice, sometimes without any hope of reward. Experiments show even young children choose to help long before they understand rules or society. Something in us seems drawn toward cooperation, but its origins remain unclear. Did it arise from survival pressures or from something deeper? A moral instinct written into our minds. The willingness to help strangers remains one of humanity's most beautiful and most mysterious traits. Civilizations rise and fall, but the deep forces behind them remain debated. Across history, mighty civilizations have grown, flourished, and then collapsed. The Maya, the Indus Valley, Mesopotamia, Rome, all rose to greatness only to fall. But why civilizations follow this arc remains debated. Some point to climate, change, droughts, and disasters. Others to war, corruption, or the exhaustion of resources. Still others believe civilizations carry within them patterns of growth and collapse, cycles that repeat regardless of time and place. The truth may be all of these or something else entirely. What is striking is how sudden collapse can be. Great cities are abandoned. Knowledge is lost. Generations vanish into silence. Civilization itself is fragile, and the forces that make it thrive or fail are not fully understood. We live within vast, complex societies. But history reminds us that nothing lasts forever, and the reasons why remain mysterious. Human curiosity drives us, but its source is still unknown. Why do we wonder? Why do we look up at the stars and ask questions no other creature seems to ask? Curiosity is one of humanity's defining traits, but where it comes from remains unclear. Some say curiosity is an extension of survival, helping us seek food, shelter, and safety. Others believe it grew as an evolutionary advantage, pushing us to explore, invent, and imagine. But curiosity often goes far beyond survival. It drives us to study galaxies billions of light years away, to decode ancient languages, to ask questions with no practical answer at all. Children show curiosity from the very beginning, reaching for the unknown, asking endless questions. It seems built into us. But why this hunger for knowledge? Why this restless drive to understand is not yet explained. Curiosity pushes us forward, shaping science, art, and exploration. But its source, The spark behind the question why is still one of life's mysteries. Storytelling is universal, but no one knows why we need it. Every culture tells stories. Around fires, on stages, in books, in films, humans shape words into narratives. Stories carry heroes and villains, struggles and triumphs. They entertain, they teach, they inspire. But why are they universal? Some suggest storytelling is a way to pass on knowledge, wrapping lessons in memory. Others think it binds communities, giving people shared myths and values. Some see it as practice, rehearsing challenges and choices safely in imagination. But stories often go beyond these roles. They create worlds that never existed. They fill us with emotions for people who are not real. They linger in our minds for years. No other species does this. Why do humans need stories? Why do we long for them again and again? We do not know. What we do know is that storytelling is as ancient as language itself, a thread running through every culture. Lightning sometimes forms glowing balls of fire, and we do not know how. Most people know lightning as a flash in the sky, a jagged streak followed by thunder. But there is a far stranger phenomenon that has baffled observers for centuries: ball lightning. Instead of a quick bolt, it appears as a glowing sphere of light, floating silently, drifting across fields or even inside homes. Witnesses describe orbs the size of a grapefruit, glowing orange, white, or blue, sometimes lasting several seconds before vanishing or exploding with a pop. For centuries, ball lightning was dismissed as myth, a trick of the eyes. But in recent years, credible sightings and even a few scientific recordings suggest it is real. The problem is, no one knows what it is. Some theories describe plasma trapped by electromagnetic fields. Others imagine vaporized silicon glowing after a strike. Some suggest chemical reactions sparked in the air. But no explanation fits every account. Ball lightning drifts through history as one of nature's strangest mysteries. Earthquake lights appear in the sky, and no one knows what causes them. During some powerful earthquakes, witnesses report glowing lights in the sky. They take many forms: flickering blue flames along the ground, flashes like lightning above cities, strange orbs floating over fault lines. These earthquake lights have been described for centuries, but modern cameras have also captured them, confirming they are real. What causes them remains unknown. One theory suggests that stressing rocks during an earthquake releases electrical charges, sparking light in the air. Another idea is that tectonic forces ionize gases near the ground, making them glow. But not every earthquake produces lights, and the appearances vary wildly. In some cases, the lights arrive before the earthquake, leading to speculation that they could act as a warning system. But their rarity and unpredictability make them difficult to study. Earthquake lights are among the most eerie natural mysteries, flashes of otherworldly glow in the midst of chaos. Some volcanoes erupt with terrifying force, and the triggers remain mysterious. Volcanoes are among the most destructive forces on Earth. Most eruptions are dramatic but manageable. Lava flows, ash blooms, small explosions. But every so often a volcano erupts with unimaginable fury, blasting enough material into the sky to alter climate and spread devastation across continents. What makes some eruptions so catastrophic? Scientists know pressure builds as magma rises and gases expand, but the exact tipping point remains uncertain. Some volcanoes sit dormant for centuries, then erupt without warning. Others rumble and smoke for years but never explode. The mystery lies in what flips the balance from silence to disaster. Events like Krakatoa in 1883, Tambora in 1815, and Mount Toba 74,000 years ago unleashed energy rivaling nuclear weapons. Toba may have nearly wiped out humanity. Yet modern science still cannot predict which volcanoes will erupt this way or when. Volcanoes are reminders that Earth itself is alive and capable of mysteries we have yet to master. Why plate tectonics began on Earth is still debated. The surface of our planet is alive with motion. Continents drift, mountains rise, oceans open and close, all driven by the movement of tectonic plates. Without plate tectonics, Earth would not have its landscapes, its earthquakes, or its volcanoes. Life itself may depend on this restless churning. But why did it begin here and not on other planets? Mars and Venus have no active tectonics. Their crusts are stagnant, locked in place. Somehow, billions of years ago, Earth's crust fractured into giant plates that slide and grind endlessly. Did water act as a lubricant, weakening rock and allowing movement? Did internal heat reach just the right balance? Or was it triggered by ancient impacts that cracked Earth's crust? We do not know. Computer models offer competing answers, but none explain why Earth alone developed this feature. Without plate tectonics, the carbon cycle that regulates climate might fail. Plate tectonics is what makes Earth dynamic and habitable. Yet the reason it began remains an unsolved puzzle. The origin of Earth's water is still uncertain. Water covers most of Earth, filling oceans, rivers, and clouds. It is essential to life. Yet its origin remains one of science's great mysteries. Did water arrive on asteroids and comets delivered during the chaos of the early solar system? Some evidence supports this, as many space rocks contain ice. But the chemical fingerprints of Earth's water do not always match those of comets. Another idea is that water was present from the beginning, trapped deep within Earth's mantle, slowly rising to the surface over eons. Perhaps both are true. Some water born here, some brought from space, but the balance is still debated. What we do know is that Earth is unusual. Neighboring planets like Venus and Mars are dry, their water lost or locked away. Something about Earth allowed oceans to gather and remain stable. Water is so ordinary that we forget its strangeness. Every drop carries the mystery of its origin. The far side of the moon looks strangely different, and we do not know why. For millennia, humans saw only one face of the moon. The far side remained hidden until spacecraft revealed it in the 20th century. What we saw was surprising. The near side, the face we know, is covered with dark maria, vast plains of cooled lava. The far side looks nothing like it, rugged, mountainous, with almost no maria at all. Why should the two faces of the same moon be so different? One idea suggests the moon once had uneven heating, with Earth's gravity creating tidal forces that warmed one side more than the other. Another proposes that an ancient collision reshaped one hemisphere but not the other. Some theories involve internal dynamics, differences in crust thickness or volcanic activity, but no explanation fits perfectly. The moon should be symmetrical, yet it is not. Its hidden face carries scars and secrets that defy simple answers. Even now, as spacecraft orbit and landers touch its surface, the far side of the moon keeps its mystery. Earth's core powers a magnetic field, but the details remain unclear. Deep beneath our feet, more than 3,000 kilometers down, lies Earth's core. a ball of molten iron and nickel surrounding a solid inner sphere. Its motion generates Earth's magnetic field, shielding us from solar winds and cosmic radiation. Without it, our atmosphere might be stripped away, leaving Earth barren like Mars. But despite its importance, we do not fully understand how it works. We cannot drill to the core, so we rely on indirect clues: seismic waves, magnetic records, computer models. We know the outer core flows like a liquid and that this motion powers the geodynamo. But why Earth's field sometimes weakens, wobbles, or reverses entirely is still uncertain. Other planets puzzle us further. Mars once had a magnetic field but lost it. Why did Earth keep its protective shield while Mars did not? The beating heart of our planet remains hidden from direct study. We feel its effects every day, in compasses, in auroras, in our very survival. But its inner workings remain mysterious. Earth's magnetic poles sometimes flip, and the cause is still unknown. Every so often in Earth's history, the magnetic poles switch places. North becomes south. South becomes north. These reversals are recorded in ancient rocks, showing a flip-flop pattern stretching back millions of years. The last full reversal happened about 780,000 years ago. But why do they happen? Scientists believe turbulence in the liquid outer core, the engine of Earth's magnetic field, sometimes becomes unstable, causing the field to collapse and rebuild in the opposite direction. But the exact trigger is unclear. Sometimes the flips are quick. Sometimes they take thousands of years. Sometimes the field only weakens without fully reversing. The mystery deepens when we consider the effects. During a reversal, the field weakens, exposing Earth to more radiation from space. Would that disrupt ecosystems? Did past reversals influence evolution? We do not know. All we know is that Earth's magnetic field is not permanent. One day, North will again become South, and the reason why remains hidden in the depths. Ice ages come and go, and we still do not know what drives them. For millions of years, Earth's climate has swung between ice ages and warmer periods. Vast glaciers have advanced and retreated, carving landscapes and reshaping continents. But why this cycle happens is still debated. Some explanations point to changes in Earth's orbit and tilt, known as Milankovitch cycles, which alter how sunlight reaches the planet. Others suggest volcanic eruptions, shifting ocean currents, or carbon dioxide feedback loops. Perhaps all of these combine in ways we do not yet fully understand. What is certain is that the rhythm of ice and thaw has shaped human history. Our ancestors migrated, adapted, and survived in the shadows of glaciers. Civilizations rose as climates warmed. But the underlying cause, the engine of these repeating freezes, remains unclear. The ice ages remind us that Earth's climate is never fixed, but part of a mystery far larger than ourselves. Mass extinctions strike suddenly, and their causes remain unsettled. 5 times in Earth's history, life has nearly been wiped out. The dinosaurs' extinction 66 million years ago is the most famous. But even greater catastrophes came before, like the Great Dying 250 million years ago, when most life on Earth vanished. Asteroid impacts, supervolcanoes, climate shifts, and change in oceans have all been proposed as causes. Sometimes the evidence points clearly, as with the asteroid that struck at the end of the Cretaceous. Other times it is murky, multiple disasters overlapping, creating cascades of collapse. Why some species vanish while others survive is equally mysterious. Why did mammals endure the asteroid strike while dinosaurs perished? Why do some extinctions unfold in slow decline while others happen in a geological instant? Mass extinctions are reminders of life's fragility, but also of its resilience. Each one cleared the stage for new forms of life to rise. But the forces behind them, sudden, devastating, and unpredictable, remain only partly understood. Saturn's rings appear young, and we do not know how they formed. Saturn's rings are among the most breathtaking sights in the solar system. Vast bands of shimmering ice and dust encircling a giant planet. They stretch for hundreds of thousands of kilometers, yet are astonishingly thin, sometimes only a few dozen meters deep. For centuries, we assumed they were as old as Saturn itself, more than 4 billion years. But recent evidence suggests otherwise. The rings appear strangely clean, made mostly of bright ice with little dust. If they were ancient, they should be darker, dirtied by micrometeorite impacts over eons. Measurements from NASA's Cassini spacecraft hinted that the rings may be only a few 100 million years old, a blink of an eye in cosmic time. If true, how did they form so recently? Perhaps a moon wandered too close and was torn apart by Saturn's gravity. Perhaps comets or asteroids shattered, leaving debris that spread into rings. But no explanation is certain. Saturn's rings may be temporary, destined to fall into the planet over the next 100 million years. We are living in the brief era when Saturn wears this dazzling crown. Uranus spins on its side, and no one knows why. Among the planets, Uranus is bizarre. Instead of spinning upright like Earth, it rolls through space on its side. Its axis is tilted by 98 degrees, leaving it rotating almost horizontally. For part of its orbit, one pole points directly at the sun, bathing that hemisphere in decades of sunlight, while the other lies in darkness. How did Uranus end up this way? The leading idea is that long ago, a colossal impact with a protoplanet knocked it onto its side. But such a collision should have left behind signs like a large moon or a scar in its atmosphere. Another theory suggests multiple smaller impacts slowly tilted the planet. Still others propose that gravitational interactions with giant planets in the early solar system pulled Uranus into its strange posture. Whatever the cause, Uranus remains unique. Its sideways spin creates bizarre seasons and may even influence its magnetic field, which is also oddly tilted and offset. No probe has visited Uranus since Voyager 2 in the 1980s. Until we return, Uranus rolls quietly on its side, carrying a cosmic riddle. Venus rotates backwards, and its strange past is still debated. Venus, often called Earth's twin, is nearly the same size and mass as our planet. But it is also profoundly strange. One of its oddest features is its rotation. While most planets spin in the same direction they orbit the Sun, Venus rotates the other way. On Venus, the Sun rises in the west and sets in the east. Even stranger, a single day on Venus lasts longer than its year. How did this happen? One idea is that Venus was struck by a massive object early in its history, flipping its spin. Another suggests tidal interactions with the Sun slowly reversed its rotation. Still, another theory imagines Venus once spun rapidly like Earth, but its thick atmosphere and internal dynamics gradually slowed and reversed it. No theory fully explains the planet we see today. Its atmosphere, dense with carbon dioxide and sulfuric acid, may hold clues, but for now, Venus keeps her secrets. Beneath her perpetual clouds, Venus turns slowly backwards and against expectation. Neptune is full of storms we do not fully understand. At the edge of the solar system, Neptune howls with winds faster than any on Earth, reaching nearly 2,000 kilometers per hour. Vast storms swirl across its deep blue atmosphere, appearing and vanishing in ways that baffle scientists. The most famous, the Great Dark Spot, was discovered by Voyager 2 in 1989. It was a storm the size of Earth. But when the Hubble Space Telescope looked a few years later, it had disappeared completely. Other dark spots have since appeared, shifting across the planet, sometimes breaking apart or fading without warning. Why does Neptune, so far from the Sun, have such violent weather? Its distance means it receives little solar energy. Some believe Neptune's internal heat drives the storms. Others think dynamics in its atmosphere amplify small changes into massive tempests. But the details remain unclear. Neptune remains a distant storm world, visited by only one spacecraft. Its mysterious weather shows us that even in the frozen reaches of the solar system, chaos can reign. Jupiter's Great Red Spot has raged for centuries, and its future is uncertain. For as long as humans have pointed telescopes at Jupiter, the Great Red Spot has swirled in its atmosphere, a storm so large it could swallow Earth whole. It has been raging for at least 350 years, perhaps much longer. But why it began and why it has lasted so long remain mysteries. The storm is an anticyclone, spinning counterclockwise in Jupiter's southern hemisphere. Powered by the planet's immense atmosphere, it seems almost eternal. Yet, in recent decades, scientists have noticed it is shrinking. Once wide enough to fit 3 Earths across, it now spans barely more than 1. Some predict it may fade away entirely in the coming century. Why did the storm form where it did? Why has it lasted centuries when storms on Earth last only days or weeks? Will it truly vanish? Or will it revive itself in cycles we do not yet understand? The Great Red Spot is a cosmic paradox, at once ancient and fragile. Comets cluster in a distant cloud we have never seen directly. Comets, with their glowing tails, have fascinated humans for millennia. They swoop in from the edges of the solar system, loop around the sun, and vanish again into the dark. Astronomers believe these icy wanderers come from a vast reservoir far beyond Pluto, the Oort cloud. The Oort cloud is thought to contain trillions of icy bodies, leftovers from the birth of the solar system. It stretches so far that its edge may blend into interstellar space. Yet despite being the source of comets, it has never been observed directly. The objects are too small, too distant, and too faint. We know the Oort cloud only from the comets it sends us, visitors that hint at the vast, unseen population beyond. Was it formed by the scattering of early planets? Does it extend farther than we imagine? We do not know. The Oort cloud is the great unseen frontier of our solar system, a ghostly shell surrounding us, full of secrets. Many moons hide oceans beneath their ice, but we do not know what lives there. Beyond Earth, water is not rare. Moons like Europa, Enceladus, and Titan all hide oceans beneath shells of ice. Some of these oceans may be larger than all the seas on Earth combined. They are kept liquid by the gravitational pull of their planets, which kneads the moon's interiors and generates heat. What makes these oceans exciting is their potential for life. On Earth, where water exists, life almost always follows. Hydrothermal vents deep in our seas thrive with creatures independent of sunlight. Could similar ecosystems exist beneath alien ice? We have hints. Enceladus sprays plumes of water into space, rich with organic molecules. Europa's cracked surface shows signs of activity below, but we cannot yet see into these oceans directly. What strange forms of life might swim there? Simple microbes or something far more complex? Until we explore these hidden seas, the answer remains locked beneath ice. Enceladus sprays water into space, and we do not know what stirs below. Saturn's small moon, Enceladus, looks unassuming, just a bright icy sphere. But when NASA's Cassini spacecraft flew past, it discovered geysers erupting from cracks near the South Pole, spraying water vapor and ice grains far into space. These plumes contained salts, organics, and even signs of chemical reactions that on Earth would hint at habitability. Beneath the surface, Enceladus hides a global ocean, kept warm by Saturn's tidal pull. The geysers may be vents connecting this ocean to the surface. But what drives the eruptions? Are they powered by hydrothermal vents at the seafloor, like those on Earth's oceans that teem with life? Or are they fueled by some other unknown process? Enceladus is small, barely 500 kilometers across, yet it has become one of the most promising places to search for life beyond Earth. Its plumes offer a direct sample of its hidden sea. But until we return with new missions, the mystery of what stirs beneath its ice remains unsolved. Titan has seas of methane, and something keeps replenishing them. Titan, Saturn's largest moon, is a world both familiar and alien. It has lakes and seas, rivers and rain. But instead of water, they are made of liquid methane and ethane. Titan's skies are hazy, its surface sculpted by weather utterly unlike Earth's. Here is the mystery. Methane in Titan's atmosphere should be destroyed by sunlight over time. If that were the case, the methane seas would have long since vanished. Yet they are still there. Something deep underground or hidden within Titan's chemistry keeps replenishing them. Some suggest cryovolcanoes may release methane from Titan's interior. Others imagine chemical processes we do not yet understand. Intriguingly, some researchers note that methane is also a potential biosignature, a sign of life. Could Titan's methane be biological in origin? We do not know. Titan's methane cycle mirrors Earth's water cycle in eerie ways, but the source that sustains it, the hidden pump that keeps its seas full, remains a mystery. Mars once had flowing rivers, but we do not know where the water went. Billions of years ago, Mars was a very different world. Vast river valleys carved the surface. Deltas and lake beds mark where water once pooled. The planet may even have had oceans. Today, it is dry and frozen, with only thin wisps of water vapor in the air. What happened to all that water? Some may be locked as ice beneath the surface. Some may be trapped in minerals. Much of it may have escaped into space when Mars lost its protective magnetic field. But the full story is unclear. Mars is littered with evidence of its watery past, yet its present is a desert. Did the water disappear slowly or in sudden shifts? Could liquid water still flow underground today, hidden from our view? The fate of Mars's rivers remains one of the greatest planetary mysteries. To solve it may be to understand whether the planet once supported life, and whether it still could. Mathematics describes the universe with uncanny accuracy, but we do not know why. Mathematics is a language of patterns, a human invention built from numbers, symbols, and logic. Yet astonishingly, it describes the universe with almost perfect precision. Equations dreamed up on paper turn out to govern stars, atoms, and galaxies. Einstein's equations predicted black holes before anyone had seen one. Maxwell's formulas describe radio waves long before they were detected. Why should abstract symbols map so exactly onto reality? Some scientists argue that math is discovered, not invented, that it reveals truths built into the structure of the cosmos. Others suggest math is a tool shaped by human minds, tuned by evolution to fit the patterns we see. But neither answer explains the eerie accuracy of mathematics in physics. Why should the same formulas describe both the arc of a thrown ball and the motion of distant planets? Mathematics is at once a human creation and a universal key. Why it works so uncannily well remains one of the deepest mysteries of existence. The constants of nature seem fixed, yet their values remain unexplained. Every law of physics rests on constants: the speed of light, the charge of an electron, the strength of gravity. These numbers define how the universe works. Change them slightly, and stars might never form. Chemistry might not exist. Life might be impossible. But why do they have the values they do? Scientists measure these constants with exquisite precision, but no theory explains why they are what they are. Some suggest they are simply accidents of our universe. Others imagine a multiverse where countless universes exist, each with different values, and we just happen to live in one where life is possible. But these remain speculations. The constants of nature are like settings on a cosmic dial, fixed, precise, and unexplained. They are the background music of the universe, a melody we can hear but not compose. We do not know if true randomness actually exists. Flip a coin, roll dice, shuffle cards. Randomness seems obvious. Yet physics makes the question stranger. At the quantum level, particles behave unpredictably. An electron may appear here or there. A radioactive atom may decay now or later, with no cause we can see. Is this true randomness, or just complexity beyond our understanding? Einstein famously resisted the idea, saying God does not play dice with the universe. He believed hidden laws must govern quantum events. But decades of experiments suggest otherwise. Quantum mechanics really may be irreducibly random. Still, some scientists believe deeper rules are waiting to be discovered. Others think randomness is woven into the very fabric of reality. If true randomness exists, then uncertainty is not just ignorance. It is part of what reality is. Whether the universe is fundamentally ordered or truly random remains an unanswered question at the heart of physics. Time itself is still one of science's greatest mysteries. We live in time. We feel it flow, second by second, carrying us from past to future. Yet science cannot fully explain what time is. Einstein showed that time is not absolute. It bends and stretches depending on speed and gravity. A clock on a mountain ticks faster than one at sea level. A clock in orbit ticks differently than one on Earth. Time is woven with space into a single fabric. But why do we experience it as a one-way arrow? Why does the past feel fixed while the future remains open? Some physicists think the arrow of time is tied to entropy, the tendency of disorder to increase. But this only pushes the question back. Why was the universe born in such an ordered state? Others suggest time itself might be an illusion, a trick of human perception. Time governs every heartbeat, every thought, every life. Yet, its true nature remains one of the most profound mysteries we face. Matter exists, but antimatter nearly vanished, and we do not know why. When the universe began, the Big Bang should have created equal amounts of matter and antimatter. But when matter and antimatter meet, they annihilate into pure energy. If they had been perfectly balanced, everything should have disappeared in a flash, leaving no stars, no planets, no people. Yet here we are. Somehow, matter won. Why did matter gain the upper hand? Experiments show that matter and antimatter behave almost identically, but with tiny asymmetries. These slight differences may have tilted the balance in the early universe, but they do not seem large enough to explain why anything exists at all. Somewhere in the physics of the early cosmos lies the reason why there is something instead of nothing. Until we find it, the victory of matter over antimatter remains an unsolved riddle. Particles have mass, but we still do not know what gives it to them. Everything around us has mass, from stars to sand to our own bodies. But what gives particles mass at all? For decades, this was one of physics' biggest mysteries. The discovery of the Higgs boson in 2012 confirmed that an invisible field pervades the universe. As particles move through it, they acquire mass, like swimmers pushing against water. Without this field, matter as we know it could not exist. But the Higgs mechanism answers only part of the question. Why does the Higgs field itself exist? Why does it have the strength it does? And why do different particles interact with it so differently? The Higgs discovery opened the door, but behind it lies a deeper mystery. Mass feels solid and obvious, but its origins remain partly hidden in the invisible fields of the cosmos. Reality may be continuous, or it may be pixelated, and no one knows. To our eyes, reality feels smooth. Space seems infinitely divisible, like a line you can cut forever. But at the smallest scales, physics may be different. Some theories suggest the universe is pixelated, made of tiny, indivisible units, like the pixels on a screen. This smallest length, the Planck scale, is far beyond what we can observe. But it might be the foundation of everything. If reality is pixelated, then space and time themselves are not smooth, but granular. The rules of physics would need rewriting. But so far, no experiment has confirmed this. Whether the universe is continuous or digital remains one of the strangest questions in science. The answer could reveal the true texture of reality itself. There may be a smallest possible length of space, but we have not found it. Physics pushes us to ever smaller scales. Atoms, once thought indivisible, were split into protons and electrons. Protons themselves turned out to be made of quarks. Yet, at some point, there may be a smallest length, a limit beyond which smaller has no meaning. This is thought to be the Planck length, unimaginably tiny, about 10 to the power of -35 meters. At this scale, space may no longer be smooth but foamy and uncertain, a quantum haze. But no experiment can reach it yet. If space has a smallest unit, then the universe is not infinitely divisible. Reality would have a bottom floor, the smallest brick of existence. Whether such a limit exists remains one of the deepest mysteries of physics. The laws of physics could have been different, but no one knows why they are what they are. The universe runs on laws: gravity, electromagnetism, quantum mechanics. They are elegant, precise, and consistent, but they could have been otherwise. Why this set of laws and not another? Why a universe where stars can form instead of one where matter collapses or drifts apart? Some scientists imagine countless universes, each with different laws, and ours is simply one where the conditions allow life. Others think deeper principles, still unknown, fix the laws in place. But for now, The origin of the laws themselves remains unexplained. We can describe the rules. We cannot yet explain why these rules and not others are written into reality. Perhaps the greatest mystery of all is whether we will ever truly understand any of this. We do not know why we yawn or why yawning is contagious. Yawning is one of the most common human behaviors, yet its purpose remains unclear. We yawn when tired, when bored, even when we see someone else yawn. The contagion is so strong that ranting about yawning can trigger one. But why? One theory suggests yawning cools the brain, increasing alertness by regulating temperature. Another proposes it increases oxygen intake, though evidence for this is weak. Still others believe yawning is a social signal, a way to synchronize group behavior or communicate a need for rest. What makes yawning even stranger is its presence across species. Fish yawn, birds yawn. Even unborn babies yawn in the womb. If it serves such an important function, why has evolution not made its purpose clear? The contagious nature of yawning suggests it may have social roots, but we still do not understand the mechanism. Why seeing someone yawn makes us yawn remains a puzzle hidden in our neurology. The placebo effect works, but we cannot fully explain its limits. The placebo effect shows us that the mind can influence the body in powerful ways. Sugar pills can reduce pain. Fake surgeries can improve symptoms. Even the color of a pill can affect how well it works. But the placebo effect has limits we do not understand. It works better for some conditions than others. Pain and depression respond well. Infections and cancer do not. Why? Some think it is because the placebo taps into the body's natural regulatory systems, things like pain perception and immune function. But it cannot create responses the body does not already have. Yet even this explanation feels incomplete. The placebo can trigger measurable biological changes, releasing endorphins and altering brain activity. How belief translates into physical healing remains mysterious, and why some people respond strongly while others show no effect is still unknown. The boundary between mind and body is less clear than we once thought, and the placebo effect stands at that blurry edge. Some people never forget anything they experience, and we do not know why. Most people forget the details of their daily lives. What you ate for lunch 2 weeks ago. What you wore last Thursday. These memories fade naturally, but a rare group of people, those with highly superior autobiographical memory, remember everything. Give them a date from decades past, and they can tell you what day of the week it was, what the weather was like, what they did that day. Their memories are vivid, automatic, and seemingly endless. What makes this possible? Brain scans show some differences in structure, particularly in regions involved in memory and perception. But the full explanation remains elusive. Is it a difference in how memories are encoded, or in how they are stored and retrieved? Interestingly, these individuals often describe their gift as a burden. They cannot forget painful moments or trivial details. Their minds are constantly flooded with the past. Why some brains develop this ability while most do not is a mystery that challenges our understanding of memory itself. We still do not know why some people are left-handed. About 10% of humans are left-handed, a ratio that has remained stable across cultures and throughout history. But why? Handedness seems to be influenced by genetics, but no single gene determines it. Brain structure plays a role, with language and motor control distributed differently in left-handed people. But this does not explain why left-handedness persists. From an evolutionary perspective, being in the minority can be disadvantageous. Yet left-handedness has not disappeared. Some researchers suggest it offers advantages in certain situations, like combat or sports, where the element of surprise matters. Others propose it is simply a byproduct of how the brain develops, a natural variation with no particular purpose. What makes the mystery deeper is that handedness appears unique to humans. Other primates show preferences, but not the consistent population-level pattern we see in people. Why humans evolved this trait and why it remains at roughly 10% is still unexplained. No one knows why humans have chins. Look in a mirror and you will see something unique among all primates: a chin. That bony protrusion at the bottom of your face exists in no other species. Even our closest evolutionary relatives, Neanderthals, had receding chins. So why do modern humans have them? Scientists have proposed several ideas, but none are conclusive. One theory suggests the chin is a structural adaptation, helping the jaw withstand the forces of chewing. Another proposes it is a byproduct of changes in our face and skull as our brains grew larger. Still others think the chin may have evolved as a social signal indicating health, maturity, or attractiveness. But the evidence for any single explanation is weak. The chin may simply be an accident, a feature that rose as our faces evolved for other reasons and just happened to stick around. It serves no obvious function today. Yet every human has one. The chin remains one of the strangest and most overlooked mysteries of human anatomy. We do not understand why humans lost most of their body hair. Humans are nearly hairless compared to other primates. We have retained hair on our heads, underarms, and pubic regions, but lost the thick fur that covers most mammals. Why? Several theories attempt to explain this. One suggests that losing hair helped early humans regulate temperature while hunting in the hot African savanna. Less hair meant more efficient sweating and cooling. Another idea is that hairlessness reduced parasites like lice and ticks, improving health. Still another proposes that smooth skin became a signal of health and attractiveness, driving sexual selection. But none of these fully explains the pattern of where we kept and lost hair. Why retain thick hair on our heads? Why develop more hair during puberty? The evolution of human hairlessness is more complex than simple adaptation to heat. It may involve multiple factors, cultural practices, and sexual selection in ways we still do not fully understand. Fingerprints are unique, but we do not know why we have them. Every human has a unique pattern of ridges and whorls on their fingertips. No two fingerprints are exactly alike, not even on identical twins. But why do we have them at all? One common idea is that fingerprints improve grip, helping us hold on to objects. But research shows the effect is minimal and may even make surfaces more slippery when wet. Another theory suggests they enhance our sense of touch, amplifying vibrations as we brush our fingers across surfaces. This seems more promising, but it is not proven. Still, others propose fingerprints help channel away water, improving grip in wet conditions. The uniqueness of fingerprints is equally mysterious. They form in the womb as the fetus develops, shaped by a combination of genetics and random physical forces. But why this process creates a pattern so distinct that it can identify individuals remains unclear. Fingerprints are so familiar we rarely think about them. Yet their purpose and uniqueness are still unsolved mysteries. The appendix seems useless, but it may serve a purpose we are only beginning to understand. For decades, the appendix was considered a vestigial organ, a useless remnant of our evolutionary past. It is a small pouch attached to the intestine, and when it becomes infected, it is simply removed. But recent research suggests the appendix may not be useless after all. Some scientists believe it serves as a reservoir for beneficial gut bacteria. When illness wipes out the microbiome in the intestines, the appendix may help reseed it, restoring healthy bacterial populations. Evidence for this comes from the fact that the appendix has evolved independently in multiple mammal lineages, suggesting it serves a function. But if this is true, why do people who have their appendix removed live perfectly normal lives? The appendix may play a minor role that becomes important only in certain situations, or it may be transitioning from useful to obsolete over evolutionary time. Its true function, if any, remains debated. We do not know why humans are the only animals that blush. Blushing is a uniquely human trait. When we feel embarrassed, ashamed, or self-conscious, blood rushes to our faces, turning our cheeks red. No other animal does this. But why? Charles Darwin called blushing the most peculiar and most human of all expressions. He suggested it evolved as a social signal, a way to show others that we recognize we have violated a social norm. Blushing may act as an apology, reducing conflict and maintaining group harmony. But this does not explain why the response is involuntary and often unwanted. We cannot control blushing, and it often makes embarrassment worse. Some researchers think blushing may be a byproduct of our complex social brains, an accidental side effect of the systems that make us aware of how others perceive us. Whatever its origin, blushing reveals something deep about human nature. We are the only species that cares so much about what others think that our bodies betray our feelings. The human brain uses more energy than any other organ, and we do not know why. Your brain makes up only about 2% of your body weight, but it consumes roughly 20% of your total energy. This is an enormous investment, far more than any other organ. Why does the brain need so much fuel? Most of the energy is used to maintain the electrical signals between neurons, the constant chatter that underlies all thought, sensation, and movement. But even at rest, when you are doing nothing, the brain still consumes vast amounts of energy. This baseline activity, sometimes called the default mode network, remains mysterious. What is the brain doing when it is not focused on a task? Some think it is consolidating memories, running simulations, or maintaining the sense of self. But the full answer is unknown. The brain's massive energy consumption suggests that whatever it is doing must be essential. Yet why it evolved to be so costly remains one of the puzzles of human biology. We still do not know why humans walk upright. Humans are one of the few mammals that walk on two legs. Bipedalism defines us, freeing our hands to use tools and carry objects. But the evolution of upright walking is still not fully understood. One theory suggests bipedalism evolved to help early humans see over tall grass on the savanna, spotting predators and prey. Another proposes it was more energy efficient for traveling long distances. Still another suggests it helped regulate body temperature by reducing the surface area exposed to the sun. Each idea has merit, but none fully explains why humans became so committed to walking on two legs. Bipedalism comes with costs. It puts strain on the spine and knees. It makes childbirth more difficult. It slows us down compared to four-legged animals. Yet we evolved this way. The transition from quadrupedal to bipedal must have offered significant advantages, but the exact pressures that drove it remain debated. No one knows why humans have such long childhoods. Humans have the longest childhood of any animal. We are helpless as infants, dependent as children, and do not reach full maturity until our late teens or early 20s. Why? One explanation is that our large brains require extended time to develop. Human brains are not fully formed at birth, and childhood provides years for learning and neural growth. Another idea is that long childhoods allow for the transmission of culture. Humans rely on learned knowledge, and extended dependence gives children time to absorb language, skills, and social norms. But this raises another question. Why not simply grow faster? Other animals mature quickly and still learn. The trade-off must be worth it. But we do not fully understand what makes the human developmental timeline so unique. Long childhoods make us vulnerable, but they also make us adaptable. The balance between these forces is still a mystery. Human skin comes in many shades, but the evolutionary pressures behind this are still debated. Human skin color varies widely across populations, from very dark to very light. This variation is primarily due to melanin, a pigment that protects against ultraviolet radiation from the sun. The standard explanation is that dark skin evolved in sunny equatorial regions to prevent sunburn and skin cancer, while light skin evolved in northern latitudes to allow more vitamin D production in low sunlight. But the story is more complex. Recent research suggests that skin color evolution may also relate to folate protection. UV radiation breaks down folate, a vitamin essential for fetal development. Dark skin protects folate in high UV environments. Light skin may have evolved as a compromise, balancing vitamin D needs with folate protection in different climates. But many questions remain. Why does skin color variation appear relatively recently in human evolution? Why do some populations not fit the expected pattern? The genetics and evolutionary pressures behind human skin color are still being unraveled. We do not know why some people can taste bitterness more intensely than others. If you have ever found certain vegetables unbearably bitter while others find them mild, you may be a super taster. About 25% of people have heightened sensitivity to bitter flavors, detecting compounds that others barely notice. This difference comes down to genetics, specifically variations in taste receptor genes. But why does this variation exist? One theory suggests that sensitivity to bitterness evolved to help detect toxins. Many poisonous plants are bitter, and those who could taste bitterness more strongly may have avoided them. But if this is true, why are not all humans super tasters? Why does the variation persist? Some researchers think there may be trade-offs. Super tasters may avoid toxins, but also avoid nutritious bitter vegetables. Non-tasters may be more adventurous eaters, but more vulnerable to poisons. The balance between these advantages may have maintained genetic diversity. But the full evolutionary story behind taste sensitivity is still incomplete. The human voice can convey emotion in ways we do not fully understand. When someone speaks, you can often tell if they are happy, sad, angry, or afraid, even if you do not understand the language. The human voice carries emotional information in its tone, pitch, rhythm, and timbre. But how we encode and decode these signals is not entirely clear. Certain acoustic patterns seem universal, High pitch and fast tempo often signal excitement or fear. Low pitch and slow tempo suggest sadness or calm. But the brain's process for interpreting these cues remains mysterious. We recognize emotion in voices automatically, without conscious thought. Infants respond to emotional tone before they understand words. This suggests the ability is deeply rooted in our biology. But why the voice evolved to be such a rich channel for emotion is still debated. It may have been essential for bonding, for coordinating group behavior, or for signaling intentions before language evolved. The emotional voice is a mystery hidden in every conversation. We still do not understand why humans cry more than any other animal. Humans are not the only animals that produce tears. Many mammals do, but only to lubricate the eyes. Humans are unique in shedding tears as an emotional response. Babies cry to signal distress. Adults cry from sadness, joy, frustration, or even relief. But why? One explanation is that crying is a powerful social signal. Tears are visible proof of emotion, hard to fake, and they elicit empathy and caregiving from others. In this view, crying evolved to strengthen social bonds and ensure support in times of need. But this does not explain why adults cry when alone, or why we cry from happiness. Another theory suggests tears release stress hormones, providing physiological relief, but the evidence is mixed. Crying remains one of the most mysterious and uniquely human behaviors. It is both a vulnerability and a strength, a window into the emotional life that defines us. No one knows why humans experience existential dread. Humans are unique in their awareness of mortality. We know we will die, and this knowledge can create a deep sense of anxiety, a feeling often called existential dread. Other animals do not seem to experience this. They may fear immediate danger, but they do not appear to contemplate their own eventual non-existence. Why do humans? One idea is that existential dread is a byproduct of our advanced cognitive abilities. The same minds that allow us to plan for the future and imagine possibilities also force us to confront the inevitability of death. Philosophers and psychologists have long grappled with this. Some suggest existential awareness drives us to create meaning, to build legacies, to connect with something larger than ourselves. But others see it as a burden, a source of suffering unique to our species. Whether existential dread serves any evolutionary purpose or is simply a side effect of consciousness remains an open question. The human ability to throw with accuracy and power is unmatched, but its origins are debated. Humans can throw objects with remarkable speed and precision. A professional baseball pitcher can hurl a ball at over 100 miles per hour and hit a target the size of a dinner plate from 60 feet away. No other animal can do this. But why did humans evolve this ability? One theory suggests throwing was essential for hunting. Early humans who could throw stones or spears accurately had a significant advantage in bringing down prey. Anatomical changes in the shoulder, wrist, and torso all seem to support throwing. But throwing may also have been important for defense, or even for social purposes, like throwing during play or competition. What makes human throwing special is not just power, but precision. We can aim. We can adjust for distance and movement. This requires extraordinary coordination between the brain, eyes, and muscles. The evolution of throwing shaped human anatomy in ways we are still discovering. We do not know why music gives us chills. Certain songs at certain moments can send shivers down your spine. Your skin prickles. Your heart races. you feel a wave of emotion. This phenomenon, sometimes called frisson, is common but mysterious. Why should sound organized in a particular way create such a powerful physical response? Research shows that frisson is linked to the release of dopamine, the same chemical involved in reward and pleasure. Certain musical features, like unexpected chord changes, dynamic shifts, or emotional crescendos, seem to trigger it. But not everyone experiences frisson, and not all music produces it. Some people get chills from music regularly. Others rarely or never do. What makes some brains more responsive to music in this way is unclear. Frisson may be tied to how deeply we engage with music, how much we anticipate and predict what comes next. But the full explanation remains hidden in the complex relationship between sound, emotion, and the brain. Some people have perfect pitch, and we do not know why. Most people perceive pitch relatively. They can tell if one note is higher or lower than another, but they cannot identify the exact note without a reference. A rare few, about 1 in 10,000, have perfect pitch. They can hear a note and immediately name it. They can sing any note on command without a reference tone. This ability, also called absolute pitch, is more common in people who start musical training very young, suggesting it may be partly learned. But genetics also play a role. Perfect pitch runs in families and is more common in certain populations. What remains unclear is why this ability exists at all. Does it offer any evolutionary advantage? Or is it simply a quirk of how some brains process sound? People with perfect pitch often describe it as automatic and effortless. But for most of us, the ability remains as mysterious as it is impressive. We still do not fully understand how anesthesia works. Every day, millions of people undergo surgery under general anesthesia. They lose consciousness, feel no pain, and remember nothing. When the drugs wear off, they wake up as if no time has passed. Anesthesia is one of the most important tools in medicine, yet we do not fully understand how it works. We know anesthetics affect the brain, disrupting communication between neurons, but the exact mechanisms remain unclear. Different anesthetics work in different ways, targeting different receptors and pathways. What they all have in common is the ability to reversibly turn off consciousness. This raises profound questions. What is consciousness if it can be switched off so easily? Why do some anesthetics cause amnesia while others do not? And why do people sometimes wake during surgery, aware but unable to move? Understanding anesthesia could teach us not only how to improve it, but also reveal deeper truths about consciousness itself. Sleep paralysis is terrifying, and we do not fully understand it. Imagine waking up unable to move. Your mind is alert, but your body will not respond. You may sense a presence in the room, feel pressure on your chest, or see shadowy figures. This is sleep paralysis, and it is deeply frightening. It happens when the brain wakes up before the body does. During REM sleep, the body is paralyzed to prevent us from acting out dreams. Sometimes this paralysis lingers after waking, leaving you trapped between sleep and wakefulness. We know this much, but many details remain mysterious. Why do so many people experience similar hallucinations during sleep paralysis? The feeling of a presence, the sense of dread, the visual and auditory distortions all seem strangely consistent across cultures. Some researchers think the brain misinterprets the paralysis as a threat, triggering fear and hallucinations. But why the experiences are so similar is still unexplained. Sleep paralysis is a window into the strange boundary between sleep and waking, a reminder of how fragile our sense of reality can be. We do not know why we have nightmares. Dreams can be strange, surreal, or pleasant, but sometimes they turn dark. Nightmares wake us in fear, leaving our hearts pounding and our minds unsettled. Why do we have them? One theory suggests nightmares are a way for the brain to rehearse threats, preparing us for danger in a safe environment. By simulating scary situations during sleep, we may be better equipped to handle real threats. Another idea is that nightmares help process trauma and stress, allowing the mind to work through difficult emotions. But if nightmares are useful, why are they so distressing? And why do some people have frequent nightmares while others rarely experience them? Nightmares may also be a side effect of how the brain processes memories during sleep. As the mind sorts through the day's experiences, negative emotions may bubble up, creating frightening scenarios. The purpose of nightmares, if they have one, remains uncertain. Some people can lucid dream, and we do not know why. Most dreams feel real while they are happening. You do not realize you are dreaming until you wake up. But some people can become aware within a dream, recognizing it as a dream while still asleep. This is called lucid dreaming, and it allows a degree of control over the dream environment. Lucid dreamers can fly, explore imaginary worlds, or face fears in a space they know is not real. Some people lucid dream naturally. Others can learn techniques to induce it. But why is this possible? The brain is supposed to be offline during REM sleep, generating experiences passively. Lucid dreaming suggests a kind of hybrid state, where parts of the brain associated with self-awareness wake up, while the rest remains asleep. Brain scans show increased activity in the prefrontal cortex during lucid dreams, but the full neurology is still unclear. Lucid dreaming blurs the line between waking and sleeping, offering a strange form of consciousness we are only beginning to understand. We do not fully understand why humans need social connection. Humans are deeply social. We form bonds, seek companionship, and suffer when isolated. Loneliness can be as harmful to health as smoking or obesity. But why is social connection so essential? One explanation is evolutionary. Early humans survived by cooperating in groups. Those who bonded with others had better chances of finding food, defending against predators, and raising offspring. Social connection became wired into our biology. But this does not explain the depth of our need. Why do we feel pain from social rejection? Why does loneliness affect physical health? Research shows that social isolation triggers stress responses, weakens the immune system, and increases inflammation. The brain treats social pain similarly to physical pain, activating overlapping regions. This suggests social connection is not just a preference, but a biological necessity. The mechanisms linking social bonds to health are still being explored, but the need itself is undeniable. No one knows why humans laugh at jokes. Laughter is a response to many things, but one of the strangest is humor. A well-timed punchline, an unexpected twist, a clever play on words can all make us laugh. But why? Theories of humor suggest it arises from incongruity, when our expectations are violated in a safe, playful way. The brain predicts what will happen next, and when that prediction is wrong in a surprising but harmless way, we laugh. But this does not explain why the response is laughter, rather than something else. And it does not account for the wide variety of humor across cultures and individuals. What one person finds hilarious, another may not. Humor seems to involve cognitive, emotional, and social elements all at once. It can bond groups, diffuse tension, and signal intelligence, but the exact mechanisms that produce laughter from humor remain unclear. Science has carried us far. We have mapped galaxies, split atoms, decoded DNA, walked on the moon. Each answer reveals more questions. Each discovery opens new mysteries. Perhaps one day we will explain consciousness, the origin of life, the birth of the universe, the nature of time itself. Or perhaps there will always be questions just beyond our reach, mysteries woven into the fabric of existence. The greatest mystery may not be the universe itself, but our place within it. Whether human minds can ever truly comprehend the totality of reality. As you drift towards sleep, you might hold that thought gently. That curiosity itself is part of the mystery. To wonder is to be human. To seek is to be alive. The questions may never end, but neither will our search. You have just traveled through 100 of science's greatest mysteries. Questions that stretch from the cells in our bodies to the edges of the universe itself. Each one is a reminder that for all we have discovered, the world remains far deeper, stranger, and more beautiful than we can fully grasp. Think of what we have touched tonight, the hidden spark of consciousness, the riddles of aging and memory, the secrets carried by oceans beneath icy moons, the timeless puzzles of stars, storms, and the fabric of reality itself. Some of these questions may be answered in your lifetime. Others may remain mysteries for generations, and still others may never be solved at all. But that is part of the wonder. To live in a universe that still holds so much unknown is to live in a universe filled with possibility. Every unanswered question is an open door. Every mystery an invitation. The fact that we do not yet know keeps science alive, keeps curiosity burning, and keeps us leaning forward into tomorrow. And as you lie here now, letting the weight of these mysteries drift across your mind, notice how gently they pull you toward rest. Like the slow rhythm of waves on a shore, the questions themselves are soothing. They do not need answers tonight. They only need to be carried, like starlight across a dark sky. Questions above, questions below, a galaxy of wonder all around you. And you, at the quiet center, resting in the knowledge that mystery is not something to fear, but something to embrace. So let your breathing fall into rhythm. Let your body grow heavy and your thoughts soften. Imagine yourself floating through the mysteries we have explored, passing by them as if through constellations in the night. Questions above, questions below, a galaxy of wonder all around you, and you at the quiet center, resting in the knowledge that mystery itself is a kind of lullaby, one that will carry you into sleep. If you happen to still be awake, you can go ahead and watch the next video when you are ready. But for now, there's nothing left to do, no answers to chase, no puzzles to solve. Just the calm certainty that the mystery itself is a kind of lullaby, one that will carry you into sleep. Good night, and may your dreams be filled with wonder.